Without any further ado, I'd like to move on to our next speaker for the day, and this is Mr. Joseph Giitter. He's Director and Division of Risk Assessment in the U.S. Nuclear Regulatory Commission in the Office of Nuclear Reactor Regulation. Very big title. Mr. Giitter develops and implements policies and guidance of the use of probabilistic risk assessments in regulatory decision-making and rule-making. His organization performs and evaluates probabilistic safety assessments for nuclear power plants. He evaluates severe accident issues as they relate to new plant designs and current generation plants. His organization also evaluates fire protection systems performances and performs and evaluates accident dose assessments. They also develop programs and conduct reviews to ensure the effective consideration of human performance, safety culture, and human factors, engineering and nuclear power plant design and operations. Mr. Giitter will be discussing risk-informed performance-based fire safety at U.S. nuclear power plants. Please welcome our next speaker, Mr. Joseph Giitter. Welcome. Thank you.
Good morning. I'm honored to be here in this beautiful country to talk about fire safety at the U.S. Nuclear Regulatory Commission. Although I'm going to be talking about risk-informed, performance-based fire safety at U.S. nuclear power plants, I believe that the use of risk insights, such as the risk insights we're using at the NRC, are an important aspect of fire safety in any country and in any program. Okay, for my overview today, I'm going to talk about a major event that led to a change in the way that the U.S. nuclear industry looked at fire safety and really set the stage for fire protection regulations in the USNRC. Then I'm going to talk about the new risk-informed performance-based regulations and give you some examples of how some of the plant modifications that have resulted from this new program have actually had benefits to protect against scenarios such as the Fukushima event. This isn't really the history of fire protection, and the title's a little ambitious, but it does kind of set the context for the history of fire protection in the U.S. nuclear industry. And it was really a landmark event. In the early days of the commercial nuclear power plants in the United States, fire protection was really viewed as more of an insurance consideration or an industrial safety concern, not really a nuclear safety concern. Although some fires had occurred at nuclear power plants, they really weren't recognized as a significant threat to the safety of the facility. The Browns Ferry event in March 22nd of 1975 changed that perspective forever. At the time of the Browns Ferry fire, Unit 1 and Unit 2 of Browns Ferry were operating, and a third unit was under construction. Units 1 and 2 shared a common control room with a cable spreading room located beneath it. The fire started in the cable spreading room at a cable penetration through the wall between the cable spreading room and the reactor building for Unit 1. A slight differential pressure is maintained across the wall, with the higher pressure being on the cable spreading room side. The original penetration seal had been breached to install additional cables required by design modifications. Site personnel were resealing the penetration after the cable installation and were checking the airflow through a temporary seal with a candle flame prior to installing the permanent sealing material. And you may ask, why were they using a candle flame? Well, in actuality, that was the standard practice in the day. They don't do that anymore, by the way. Temporary sealing material, in fact, was highly combustible. So when the flame ignited the material and caught fire. In the cable spreading room, the extent of the burning was really limited, and the fire was controlled by a combination of the installed carbon dioxide extinguishing system and manual firefighting efforts. The major damage occurred in the Unit 1 reactor building adjacent to the cable spreading room, where there was a high concentration of electrical cables. Roughly 1,600 cables were damaged. The electrical cables, after the insulation had been burned off, had actually shorted together and grounded such that control power was lost for much of the installed equipment. The reactor was safely shut down, but the emergency core cooling system for Unit 1 was rendered inoperable. So this fire affected both trains of safety system. Immediately following the fire at Browns Ferry, efforts began to assess the damage and repair Units 1 and 2. One of the biggest challenges for the utility was to redesign the cable tray penetration seal and prove to the NRC that the seal was safe. At the time of the Browns Ferry fire, however, no nationally recognized standards were available for fire testing of cable tray penetration seals. The utility constructed a full-scale model at the Watts Bar Nuclear Power Plant construction site and eventually successfully qualified the redesigned cable tray penetration seal and used this to justify the restart of Units 1 and 2 and used it as a licensing basis for Unit 3. In parallel, however, the NRC began to really take a hard look at its fire protection regulations. After the Browns Ferry fire, the NRC revised its fire protection regulations to reasonably ensure a reactor maintains the ability to shut down safely in the event of a fire. And it did this in a number of ways. One was by minimizing the potential for fires and explosions. And part of that is reducing transient combustibles in the plant. Another was to ensure that there was sufficient distance between trains of safety systems, or that there was adequate barriers between trains. Now, since many plants at the time had already been constructed, this was difficult, and in some cases impossible. And I'll talk about that a little bit later. Another requirement was means of rapidly detecting, controlling, and extinguishing fires that do occur. And then finally, ensuring that the operators can shut down the reactor safely despite a fire. So you might look at this as what we call a defense in depth. Various levels of safety, starting with preventing fires to ensuring that you can mitigate fires once they occur. The NRC's fire protection regulations have really evolved over the 38 years since the Browns Ferry fire. And today the NRC requires a rigorous fire protection program at every commercial nuclear power plant in the United States. Utilities can implement a deterministic approach or more recently adopted risk-informed performance-based approach to meet the fire protection regulations. Every plant must have a fire protection plan that satisfies the regulations, and I'm not going to get into the details here, but it's our Code of Federal Regulations that are govern the regulation of all nuclear power plants. The fire protection plan must outline the overall fire protection program, installed fire protection systems, and the means to assure that the reactor can be safely shut down in the event of a fire. Plants historically took a deterministic approach to ensure that the fire protection plan was adequate, but more recently, a risk-informed performance-based approach has been adopted into the regulation. First, I'm going to talk a little bit about the traditional deterministic approach. Plants that were licensed before January 1st, 1979 were subject to the prescriptive requirements of 10 CFR 5048B and Appendix R. These prescriptive requirements were based on an assumed serious fire where the generic criteria was established for all plants. And when we talk about deterministic requirements, we're talking about, as I mentioned before, requirements for separation of trains. It turns out to be 20 feet, or having a 3-hour fire barrier with installed suppression and detection and suppression systems. In some cases, the requirements set forth weren't practical for every plant or existing plants, or there was a more favorable approach to achieve an equivalent level of safety. So as a matter of fact, because many of these plants were already constructed, they couldn't, for example, all meet the 20-foot separation between trains requirement. So they had to apply for exemptions and in essence show an equivalent or a higher level of safety was accomplished through another means. This led to a multitude of exemptions and really complicated the fire protection licensing basis. Plants that were licensed after January 1st, 1979 were not subject to the 10 CFR 5048B or Appendix R requirements, but also used a deterministic approach. And the approach was different in that the requirements were became part of their licensing basis through license conditions. So in essence, they met the requirements in a different manner. In July of 2004, the NRC Commission added a new requirement which incorporates the National Fire Protection Association NFP 805 by reference with a few exceptions. This regulation permits licensees or utilities to voluntarily adopt a risk-informed, performance-based fire protection program. The risk-informed, performance-based approach considers risk insights as well as other factors to better focus attention and resources on design and operational issues according to their importance to safety. This approach relies on a required outcome rather than a specific process or technique to achieve that outcome. It allows utilities to focus their fire protection activities on the areas of greatest risk. 2 nuclear power plants have successfully transitioned from a deterministic licensing basis to a risk-perform basis under NFP 805. Those 2 plants were Sharon Harris, which transitioned in June of 2010, and Oconee, which transitioned in December of 2010. And those 2 plants were the pilot plants for the NFP 805 program. Currently, about half of all of the 102 operating power plants in the United States have informed the NRC of their intent to transition to NFP 805. And in fact, we have about 20 applications currently in-house that we're in the process of reviewing. In some cases, there's an economic benefit, an opportunity for future self-approval, and greater regulatory certainty with the NFP 805 approach. NFP 805 license amendment requests are being submitted on a staggered schedule because we have a finite number of staff, and it requires both fire protection staff as well as risk analysts, people who are experts in probabilistic safety assessment. And because of that, we're doing the review in a staggered approach. So we're about to issue the decisions on license amendments for the first 3 or 4 plants in the queue, and we just received applications a couple weeks ago on others. So there's about 20 plants in various stages of the process right now. And part of that is doing site audits where we go out and do walk downs of the plant and discuss the plant modifications, look at fire modeling, look at their fire PRA or PSA. So it's a very resource intensive process, but well worth the results. NFP 805 enables leveraging the state-of-the-art in fire protection evaluation techniques to maintain and enhance safety. It establishes fundamental fire protection program and design requirements for fire protection systems and features, and it allows nuclear safety performance criteria to be satisfied by using both fire modeling and fire risk evaluation. By using this approach, resources can be focused on higher risk areas. However, implementation of this method maintains a focus on defense in depth, which has proven to be a sound regulatory approach in the U.S. So just as I described before, you still have the layers of protection, the defense in depth, the emphasis on detection, the emphasis on suppression, the emphasis on fire barriers and separation, but you're doing it in a smarter way, and you're looking at those fire areas or those areas of the plant that are really more susceptible and would result in the greatest contribution to risk. In practice, plants that have gone through the NFPA 805 transition process have performed analysis that highlighted major contributors to fire risk. Based on that, they've made commitments or actually made modifications to address these major contributors to fire risk. And some of the examples, modifications, one of the biggest ones for pressurized water reactors, particularly Westinghouse plants, is loss of reactor coolant pump seal cooling. Most plants have two different means of cooling the reactor coolant pump seals, but if you do lose cooling to those seals, it can result in a loss of coolant accident. So some of the modifications that are being made under NFPA 805 look at installing passive seals, what we call shutdown seals, or having a dedicated alternate seal injection system. And that, as I'll talk about later, has addresses some of the findings from Fukushima as well. Another example is isolation of flow from auxiliary feed water pumps to steam generators and spurious opening of a safety valve. To address the loss of seal cooling for reactor coolant pumps, Sharon Harris installed a new alternate seal injection system. Oops, sorry. Here's a photograph of the alternate seal injection pump. It includes a dedicated diesel generator and a dedicated charging pump to supply coolant to the reactor coolant pump seal. And it also has additional ability to power battery chargers. The alternate seal injection pump was installed to address both fire risk issues as part of the NFPA 805 transition and to improve accident mitigation for internal and external events. So when they did their probabilistic safety assessment, this was a major contributor for fire risk, but it was also a major contributor in other areas as well. The total modification included the pump and a completely independent diesel generator, a boric acid storage tank, suction and discharge piping, and controls to make the alternate seal injection system fully automatic so that upon a loss of reactor coolant pump seal injection, the new diesel generator and associated pump would automatically start without the need for operator intervention and provide reactor coolant pump seal cooling. The utility reduced its fire risk considerably with this alternate seal injection system and with the other modifications made for NFPA 805, which are shown on the next slide. During the NFPA 805 transition process, plants have taken a systematic look at their fire protection program and analyzed the program using both traditional fire modeling and risk-based techniques. This has led to an improved understanding of the fire protection program and the sensitivity of specific aspects of the program as they relate to the specific configuration and processes unique to the particular plant. In reviewing the license application, the NRC staff also developed a more complete understanding of the aspects of the program that have had a significant impact on fire risk. Because of this improved understanding by both the utility and the NRC, enhancements could be proposed and implemented by the licensee and approved by the NRC such that the overall fire risk was reduced. Typically, these enhancements go beyond what is required in the previous licensing basis. Another method of reducing fire risk that has been utilized during the NFP 805 transitions is the installation of a very early warning fire detection system, or what we call a VUFDS. A VUFDS, or incipient fire detection system, is a system designed to detect fire precursor events such as component wiring degradation in the pre-flame or incipient fire stage, using a very sensitive fire detector element. The VUFDS typically measures obscuration, which is optical smoke density, to detect the presence of degradation or smoke. With the aspirating design, a piping system can be connected to a sample pump such that many points may be sampled using the same pump, either simultaneously or through a valving arrangement that changes sample streams periodically. This allows sensitive detection equipment to be located in a different physical location than the places being sampled. This is a diagram of the VUFDS that was used at the Sharon Harris plant, which was one of the pilots. There are many commonalities between the modifications that are being proposed or implemented for NFP 805 and those that are being implemented due to lessons learned from the Fukushima nuclear power plant disaster. Let me just summarize what happened at Fukushima, although I'm sure many of you are familiar with it. On March 11th of 2011, a magnitude 9 earthquake struck off the north coast of Japan, triggering a loss of off-site power at the Fukushima Daiichi nuclear power plant. All of the operating reactors, which at the time was 3 of the 6 boiling water reactors, tripped, and the backup emergency diesel generators started as designed. So the seismic event itself did not affect the plant. However, the tsunami, which occurred about 40 minutes after the earthquake, was far more severe than the design basis of the plant, and it flooded the plant. It took out the emergency diesel generators. So without any power, coolant water could not be injected and circulated to cool the fuel rods in the reactor. And consequently, the temperature in the reactor increased, resulting in fuel rod cladding oxidation and hydrogen production, and eventually core damage. Workers faced many challenges in their attempts to manually vent the hydrogen due to the high levels of radiation. There were multiple explosions due to increased levels of hydrogen. Additionally, operators were unable to monitor the condition of and restore normal cooling to several spent fuel pools. In fact, because of conflicting information, there was a lot of concern that one of the spent fuels had been uncovered, and it actually detracted from the attempt to provide cooling to the 3 reactors. In this diagram here, you can see the actual photo that somebody took, and you can see how high the tsunami was relative to what the design basis was, which was only 14 meters. Following the earthquake and tsunami at the Fukushima Daiichi nuclear power plant, the NRC established a senior-level task force referred to as the Near-Term Task Force. The Near-Term Task Force conducted a systematic and methodical review of all NRC regulations and processes to determine if the agency should make safety improvements in light of the events in Japan. As a result of this review, the NRC issued 3 orders to industry. One had to do with mitigation strategies for beyond design basis external events. Another was to ensure reliable hardened containment vents, and a third was enhancing spent fuel pool instrumentation. There were also another number of demands for information sent out, which we call 5054F letters. Several of the Phase 1 enhancements proposed by industry to address concerns regarding mitigation strategies for beyond design basis external events include ensuring sufficient cooling water and backup power supplies are available in the event of an unforeseen accident. In these areas, some of the proposed modifications overlap with modifications committed to during the transition to risk-informed performance-based fire protection, NFP 805. And some of those are illustrated in this chart here. So for station blackout, and station blackout is what we refer to as complete loss of AC power and DC power. So that's if you lose off-site power, your emergency diesel generators are unavailable or don't start, and as well as losing DC power. And then the other consideration is providing for pressurized water reactors. You have to, one of the means of cooling the reactor down is to have auxiliary feed water flow to the steam generators. So due to the NTTF recommendations, or near-term task force recommendations, and subsequent NRC orders, several enhancements have resulted from the lessons learned during the events of Fukushima Daiichi are currently underway. Some of the modifications that were previously identified during NFP 805 transitions intersect with the modifications being proposed to address Fukushima concerns, particularly in regard to mitigating strategies for beyond design basis external events. So that's that view graph here. You can see this is a simplified diagram, but the point is there's considerable intersection. And many licensees or utilities, we call them licensees, we're currently in the process of making the modifications for NFP 805 that in retrospect will help them with a station blackout, which is what happened at Fukushima. So for example, during the NFP 805 transition, it was identified that reactor coolant pump seals needed to be protected from degradation due to temperature excursions that may occur during a station blackout. In some cases, this protection was proposed by including a passive thermal shutdown seal. In others, it was provided by an alternate seal injection system with a dedicated diesel generator. Both options would prevent a nuclear power plant's reactor core from it would prevent a loss of coolant accident, which would threaten the reactor core by ensuring that the reactor coolant pump seal remains integral. Other NFPA transition modifications relevant to station blackout concerns from Fukushima included the addition of DC batteries and AC power supplies, and the addition of diesel-backed emergency lighting for the main control room. Some of the ongoing NFPA 805 transition license amendments have proposed changes that are also relevant to Fukushima issues, such as the addition of an additional auxiliary feed water pump. So we're seeing a whole range of modifications that will be beneficial for addressing station blackout, or even a situation where flooding were to knock out some of the traditional equipment. You'd have additional equipment available to ensure that the critical safety functions are maintained. To summarize, fire protection programs at U.S. nuclear power plants have really evolved from looking at fire safety as an industrial hazard to really having a robust nuclear safety program, which I believe we have today. However, it continues to evolve, and the most recent evolution is moving from deterministic requirements, which specifies distance between trains and fire barriers, to a risk-informed performance-based approach where you look at those fires that are most likely to result in core damage and make modifications to address those. So as a result, utilities have made substantial safety improvements. Many of these improvements are helping them address some of the vulnerabilities that we observed as a result of Fukushima, such as station blackout. That concludes my remarks, and I'll be available to answer any questions you have when we have our discussion afterwards. Thank you.